this video, I want to talk a little bit about finding the derivatives of exponential functions. You'll notice that this section topic is called logarithmic differentiation. You're probably thinking you're finding the derivatives of exponential functions and you're using logarithmic differentiation. Sounds a little weird. It does, but you'll see why in a minute. So I want to make the point here. You may not even have thought about what I'm getting ready to show you, but we actually have multiple ways of finding derivatives depending on specifically finding derivatives when we have exponents, depending on what else we have in the problem, where the variables are, that sort of thing. Take a look. If I find the derivative of x cubed, that's a power rule problem, right? That's 3x squared, okay? If I find the derivative of an exponential function where we've got a constant as the base and a variable as an exponent, that's going to be 2 to the x times the ln of 2. Totally different pattern, okay? Not a power rule problem. All right, well, so we've had a variable to a constant. We've had a constant to a variable. There are two other possibilities you could have. You could have a constant to a constant power. Hopefully everybody realizes that's just going to be a constant. The derivative of a constant is 0. So constant to a constant power has a third pattern that's totally different from the other two. All right, the final thing here would be to have a variable taken to a variable power. And the question is, I don't think the derivative is going to be 0, but the question is, would this be power rule? Would the x come down in front and you drop the power by 1? Is this something like this? Would it be something like x to the x times the ln of x? Or is it something else entirely? Okay, pretty fair question to ask. So I actually want to come back to the exponential function, something basic, maybe like 2 to the x, and I want to look at a process known as logarithmic differentiation that we're going to use to deal with exponents in cases like x to the x, okay? So we already know how to find the derivative of 2 to the x, but I want to come back to this. So you may not even remember how we proved this originally because it's been a really long time. We actually used logarithmic differentiation, and I think I just didn't tell you that's what it was because we hadn't really worked with it yet. Anyway, so the idea was I have two equal things. If I have two equal things, I could take the log of both of those two equal things and get two equal logs, right? So in other words, if y equals 2 to the x, the natural log of y is equal to the natural log of 2 to the x, okay? By the way, that's what logarithmic differentiation is. It's the idea of taking the log of both sides of an equation. Usually it's going to be situations where your variable is an exponent, okay? And that's why you're going to take the log of both sides, because you can use the log exponent rule to peel this exponent off and roll it around out in front, and then you're going to have a derivative that's a lot easier to find. Okay, now I could take the common log of both sides, but I took the natural log of both sides because that's a pretty easy derivative rule that's easy to apply. All right, so I have the natural log of y is equal to x times the ln of 2. Okay, and now I'd like to take the derivative. Okay, so I'm going to differentiate here this statement. All right, the derivative of the natural log of y, that would be 1 over y. Don't forget, this is implicit differentiation technically. I need to multiply by the derivative of the inside function with respect to x. I could call it dy dx, but to keep the notation simple here, I'm just going to call it y prime this time. It's the derivative of y, okay? On this side, it looks like you're going to use a product rule, but notice the natural log of 2 is just a constant, okay? It's about 0.693. So if I had 0.693x, the derivative would just be the constant, right? It's a power rule problem. So anyway, that's what's going to happen here. The derivative of this is just the ln of 2, okay? And that's all that's going on. Now, I want to solve for y prime. I've got this 1 over y over on the left. So I'm going to multiply both sides by y, okay? The y's cancel over here. All that stuff's gone. We've got a pretty simple equation now. The final thing, though, my original function was in terms of x. It was y equals 2 to the x. And it's kind of weird having a y in the equation here. But if you go back, if you remember, the original equation was y equals 2 to the x. Those two things are interchangeable, okay? So anywhere I see a y, I can put a 2 to the x. And so that's what I'm going to do. I'm going to pull this guy here, and that tells me that y prime is going to be 2 to the x times the ln of 2, and that was our basic pattern for the exponential function. Okay, I don't think I even called it logarithmic differentiation the first time we did it, but that's what it is, all right? So I just took the natural log of both sides and I went through. We also hadn't done implicit differentiation at the time, so it's one of those cases where I kind of had to say, hey, hang with me, you'll understand this later. And now that doesn't look so difficult, okay? Well, we're going to use implicit differentiation to address that question about x to the x, okay? So in other words, if I wanted to find y prime, and my function is y equals x to the x, and my question is it, x to the x times the ln of x, how is that going to work? Same thing, okay? I have a variable that's an exponent. If I had it in log form, I could peel that exponent off around front, and maybe I'd have something I could deal with. So I'm going to take the natural log of both sides. I'm going to take the natural log of y, and I'm going to set it equal to the natural log of x to the x. And that's going to let me pull that x around out to front, okay? So we get ln of y is equal to x times the natural log of x. Okay, remember my original function was x to the x. Okay, and now we're just going to take the derivative. We're going to differentiate this equation. Okay, so on this side, the derivative of ln of y is 1 over y, but I have to multiply by the derivative of the inside function with respect to y, and with respect to x, I'm just going to call it y prime, simpler notation. That's a product, okay? So unlike the previous example where I had a constant I could factor it out, there's a little bit more going on here, which, by the way, is why we're not going to have quite the same easy pattern for x to the x that we have with some of these other cases. So product rule says you take the derivative of the first and you multiply by the second. So it's going to be ln of x plus the first times the derivative of the second. Now that's 1 over x, okay, which is going to give me an x over x, which interestingly is going to simplify just to be 1. Okay, so that's not terribly messy. Okay, and then I want to get y prime by itself, so I'm going to multiply both sides by y. Okay, and so I'll multiply this side by y, I'll multiply this side by y as well. And so all this stuff over here is going to cancel. Same issue we had before. The original equation was written in terms of x, and suddenly this thing has a y in it. Okay, so again, that's kind of weird. But I can replace the y with the x to the x. And so my final derivative is going to be y prime equals x to the x times the ln of x plus 1. Okay? And you can distribute that if you wanted to, but I think that would be a pretty standard form to leave this in. Unfortunately, logarithmic differentiation is really going to be required to do these problems where you have a variable as your base and a variable as your exponent. Okay, if you notice, that's a little more complicated derivative than we were hoping it was going to be. Okay, it doesn't quite follow any of those other patterns. Okay, so if you've got a variable in your base and a variable in your exponent, you're going to have to go with logarithmic differentiation. All right, let's try one more of these. And actually, I'd really like you to stop the video and see if you can try the process here and then get this to work. All right, let's see here. Let's try y equals quantity x plus 1 raised to the 2x power, okay? So we're trying to find y prime, all right? We've got a variable in the base, we've got a variable in the exponent, okay? We've got both of those here. All right, so I'm going to go through my process here. I'm going to take the natural log of both sides. So ln of y is going to be equal to the ln of this whole thing over here. So that's ln of x plus 1 to the 2x power. Okay, remember the whole reason I'm doing this is that I can peel off that exponent and I can bring that 2x out in front, and I no longer have a variable that's part of an exponent. Okay, and now it's all stuff I know how to find derivatives of. So on this side, I get a 1 over y when I take the derivative times the derivative of the inside function. Okay, over here, it's going to be messy, it's a product rule. Derivative of the first term is 2 times the second is ln of x plus 1, okay, plus the first times the derivative of the second. This is going to be the reciprocal of x plus 1, and then do multiply by the derivative of the inside function, but it's just 1, so it's not going to change anything. And so you might want to write this as 2x over x plus 1. Might be a little better way, a little neater way to write that, a little more concise way to write that. Okay? Now notice, I want to isolate the y prime, so I'm going to have to multiply both sides by y. This whole thing is getting multiplied by y. Okay? So this whole thing gets multiplied by y. You're going to need parentheses. Okay? And of course, all this stuff over here is going to cancel out, and that's kind of the point. And we end up with y prime equaling, it's going to be 2 times the ln of x plus 1 plus 2x over x plus 1, all of that multiplied by the original y value, which was this. Okay, so for all of these exponential equations, you're going to get back the original expression, but then a bunch of other stuff. Okay, so we've got this x plus 1 to the 2x power. Okay, these derivatives are going to be big, they're going to be ugly. The nice thing is they're really not going to simplify a whole lot. So if you know the process and you're careful applying the product rule and you're careful simplifying things, they'll work out really nicely. It's just big and unwieldy looking, and again, they're always fun for me to grade too. But that's the basic idea. So hopefully that gives you enough of an idea of how this works that you would be able to apply this in other cases.